Welcome to The Explainer. Today, we're going to demystify a totally critical foundation of Java and object-oriented programming, encapsulation. And we aren't just looking at dry theory here either. We're going to explore this through a pretty outrageous banking scenario. So let's get ready to lock down our code.
All right, let's dive into Section 1, the Sharpie problem, also known as variable mutation.
I want you to imagine a crazy scenario for a second. You walk into your local bank branch, but instead of waiting in line, you hop right over the teller counter. You just strut past the security guards, walk straight into the main vault, pull out a thick, black permanent marker, and write 10 million right next to your name in the physical central ledger. It's an absurd thought, right? But honestly, in the software world, if your code allows direct variable mutation without access controls, that is precisely how vulnerable your application state is. Without strict boundaries, any outside class can essentially take a Sharpie to your data.
Moving right along to Section 2, the flawed blueprint, where things are public by default. So, when you're setting up a new account, a naive Java blueprint might start out looking a bit like this. Double balance equals 50.0. It looks totally innocent, but there's actually a massive flaw here. Because there isn't an access modifier listed right before the word double, this variable is just public by default. It's wide open to tampering. If you have another class, let's say my account, it can instantly reach in and change that balance to whatever it wants. It can completely corrupt the internal logic of your software in a split second. And look, allowing direct variable modification doesn't just change a number. It literally shatters the fundamental business rules of financial software. When an external class can just go in and write a new balance, it bypasses your audit trails entirely. It completely skips over any fraud prevention measures you might have carefully architected, and it ignores all validation rules. It is the exact equivalent of that bank robber jumping the counter, and in a robust system architecture, we simply cannot allow it. Okay, so how do we fix this? That brings us to Section 3, securing the vault with private fields. If you compare that original flawed blueprint to our new secure solution, you'll see we secure the vault with one single, incredibly powerful keyword, private. By changing the state to private double balance equals 100.0, we take that ledger and we lock it inside a thick steel vault. Outside classes can no longer see it, and they definitely cannot edit it directly. But of course, we still need a way for legitimate systems and customers to actually interact with their data, right?
Well, because we literally never grant external classes direct access to internal sensitive records, we use what are called getters and setters. You can think of them as strict security checkposts. Getters allow external callers to view the state safely. Setters, or action methods, allow external callers to modify the state, but only by passing through the rigorous security rules we define. The server strictly forces all external callers to execute these public methods if they want to update the application state.
Let's break this analogy down to see exactly how it works in the real world. A getter is basically like looking at your account balance on an ATM screen. You can safely read the value, but you absolutely cannot reach your arm through the glass to rewrite the digits. A setter, on the other hand, is like handing cash to a bank teller over the counter. You don't just walk in and put the money in the vault yourself. You hand it to the teller counts the bill stack, checks your account status, updates the system ledger, and only then do they adjust the vault. You are asking the system to make a change rather than forcing the change yourself.
Which leads us to Section 4, real-world API disasters and massive security risks.
Because when these guardrails are forgotten by developers, we're not just talking about academic theory anymore. We're talking about massive, real-world stakes here. According to cybersecurity benchmarks, parameter tampering and unvalidated state modification consistently rank among the top API security risks globally. When you leave setters unprotected or you don't put rigorous validation inside those methods, attackers pounce. Missing guardrails enable malicious users to trigger catastrophic integer wraparound glitches. They can literally drain digital wallets dry just by bypassing your intended business logic.
I absolutely love this little note from the professor who wrote our source material today. They added this gem. My own bank balance looks closer to a null point exception at the end of every month, but at least Java ensures our software balances are safer than my personal finances. It's just a really great reminder that while our own real-world wallets might be a bit light, our code's wallets must be completely impenetrable.
All right, let's wrap things up with Section 5, the Secure Vault Challenge. Time for some practice questions. Let's actually test this out in practice. Imagine a developer creates a public setter called setBalance. But inside that method, they just blindly write balance equals new balance. Spot the flaw here. What critical validation checks are missing? Think about what happens if a malicious external caller executes setBalance with -5,000. If your setter just blindly accepts any number without checking if it's negative, your application is completely broken. A setter is basically useless if it doesn't actually validate the data it's receiving.
So, here's an architectural challenge for you to tie this all together. Let's say you're building a Java class named Secure Vault. Step 1 is properly encapsulating a private integer called pincode set to 1234 and a private double called stored gold set to 50.0. Lock those down. Step 2 is implementing a getter for that stored gold, but requiring the correct pin code as an argument before it reveals anything. And finally, Step 3, writing the logic so that if the supplied pin is incorrect, you completely reject access and return negative 1.0.
By really understanding getters, setters, and the absolute necessity of that private keyword, you hold the keys to robust application security. You now understand exactly why direct state access is a complete disaster waiting to happen. So as you architect your next application, ask yourself, will your vault hold up against the Sharpie? Thanks so much for joining this explainer.